All right, let's go ahead and take another example here. Okay. I'm going to go ahead and just draw this right in there for us. Doesn't have to look perfect or anything. Just get the idea. Okay. I've got y is equal to the square root of x. We all know that's a tipped over parabola. I'll label that. And then I've got another line here coming through. X plus y equals 6. Okay. And then I'm going to have, once again, I'm going to have another boundary here being the x-axis, so that's y equals 0. Now the region I'm talking about integrating over is this region bounded by these 3 points, this pseudo-triangular region, look right here. Okay? All right. Everybody gets it? Yeah. Come on. It'd be this thing right here, all this. Yep. Yeah, sorry. Anyway, everybody gets it. Now, I want to do this again. I is the double integral over that region. All right, remember our notation? F of xy dA. I just write dA so there's no particular bias on which direction I'm integrating first. Okay? Fubini's theorem says we can perform this as an iterated integral. All right. Let's try the y direction first. Okay? Now, I suggest when you guys run into problems like this, one of the things I really like to do here is go ahead and find sort of the corner points of the region you're dealing with. Now, you guys can eyeball these in here. Now, to find this corner point, this is easy here. You just let y equal 0, and you can see that x is going to be 6. So we've got 0, 0, 6, 0. Where these two intersect here, you're going to have to solve two equations and two unknowns. But not to spend too much, actually my picture doesn't look that good, but not to spend too much time on it, but this point should be 4, 2. I guess it's not all that bad. Okay? All right, so you guys could work out that's algebra here. Now, what I'm going to be doing is maybe integrate in the y direction first. I guess. Now, the point of this problem is not just getting used to setting up the double integral property, but to show you that sometimes there's an advantage in setting up your integral one direction versus the other. Okay? Sometimes if you can integrate in one direction, it's really hard. Sometimes you can reverse the order of integration and make your computations, or your setup at least, easier. Okay? All right, let's try this one. Now, I want you guys to notice something here that would happen. There's a natural break right there, right? Because when I'm integrating, remember in the y direction first, let's set up our little what? Little differential change in x, then what? All these differential changes in y going up, forming that little picket here, and then I'll do the same thing over here. Do you guys see the difference in the two situations here? The upper limit, which I'm integrating to, changes from in this side versus this side. It changes after I, pass this point, 4, 2, or as far as the x value goes, 4. Okay? Alrighty? Does that make sense? Here, because the upper limit is actually this line, over here it's actually that parabola. Okay? Well, here's what we're going to do. We're going to have to break it into two double integrals. Okay? So here we go. We're integrating in the y direction first. So I'm going to write what? dy, then dx. And I know I'm going to have to do what? A second integral. The way this is set up. Okay. Let's go ahead and integrate in the over this part first here, where the upper limit is the parabola. Where is y going from? It's going from what? Y equals 0, the x-axis, up to what? Y equals the square root of x. Okay? Now, project this part that you just integrated over onto the x-axis. Where is x going from and to, right? I'd actually be partitioning from, what, 0 to 4, right? Okay. Remember, the x is 4 right here on this point. Value of x where we change from one function to the other. Okay? So that would be the double integral over that subregion for a function f of xy. And to this, we got to add whatever the integral is over this thing. Okay? Let's see. Now, let's do this. Where is y going from and to here? Y is going from 0. Now, I'm certainly not integrating over a rectangle here, so I'm going to have, if this is constant, this is going to have to be what? Variable. And since I'm integrating out y, that when I say variable, it's going to be a function of what? X. Now, the upper limit is actually this line. What is y in terms of x there? Y, it is equal to 6 minus x, right? So y is going to what? From 0 up to 6 minus x, okay? So this whole thing on the inside, this inner integral, is going to be a function of x. Now, taking this thing and projecting it onto the x-axis, where is x going from and to? Even though it doesn't look like it because my picture's lousy, it's going from what? 4 to 6. Okay? You guys notice here, x is actually going from what? 0 to 6 overall. But the fact is I had to break it into two separate integrals because the upper limits are two different functions. Now, some fancy person might say you could go from 0 to 6 and then from 0 to g of x or something like that. But that would have to be a piecewise defined function that would be of no use in an actual calculation. So this is what you're going to have to end up doing here. Okay? All right. Let's try the next direction. And maybe let me go through this again. So there's the y direction first. I'm going to redraw this because it looks kind of lousy, kind of bothering me. Let's go ahead and draw it again for your convenience. Okay, this should have a lot more tilt to it that way. And then this is y is equal to, or y plus x is equal to, x plus y is equal to 6. That is, y is the square root of x. Okay. So this was what? 4, 2. This was the origin. We got y equals 0. And this was 6, 0. Okay, let's integrate in the x direction first. Okay. You guys see this is only going to take a single integral? Okay, it's only going to take a single one. Okay, we're still dealing with the same region here. Now, I'm going to imagine that I performed a partition on both the y and the x, but I'm holding y fixed, and I'm integrating in the x direction first. So I'm going to write my picket like this. Okay, so I is equal to integral f of xy dx, and then we're going to integrate out. Now I claim we can do this in, like I said, in a single integral here. Okay, now let's integrate out y first, or x first. So we're going to be going from what? This part on the parabola to what? That line. Now, my limits of integration are going to be what? Functional, variable, right? And I'm integrating out x. So my limits of integration, maybe one is constant, but at least one of these is going to be what? A function of y. Okay, maybe both of them are. In fact, both of them are this time. Okay? Now, come over here and look at this part here. Okay? This time I'm trying to get x in terms of what? Y. X in terms of y. X is in terms of y. Oh, wait. Couldn't I say x is equal to y squared? Yeah, I sure could, right? That would be the same parabola, at least for the first quadrant. Okay? And then what? I'm integrating out to this line. What is x in terms of y there? It is equal to 6 minus y. Okay? Alrighty. Now, what am I going to need here for these? Can I have a function of x here or a function of y here? No. These are the outer limits. Okay? Those have to be what? Constants, yes. Okay? If you expect a numerical answer in the end. Okay? Where is y going from and to? We'll take this region R and project it. Just project it over onto what? What were you really partitioning? You were partitioning everything from what? 0 to 2 in the y direction. Ta-da! And there's our answer. Box in your final answer. Okay? So there it is. There's a couple examples for you. We'll be looking at more as time progresses here.